Welcome back to the Tutor Wizard. I'm Adrian. Please subscribe right here. We're doing mathematical modeling. This is Chapter 2, Discrete Time Models. Section 2.5 is going to be criteria for equilibrium stability. And this lecture specifically, what we're going to do is 3 theorems stating criterion for the stability of an equilibrium to this difference equation, which is autonomous in first order. Let's get to it. All right, theorem 1 of 3. The first one's going to say, consider this difference equation, xt plus 1 equals f of xt, where f may be nonlinear, where f is continuously differentiable. What that means is f is differentiable and the derivative is continuous, and we want x star to be in equilibrium, so we've already found them for the system, or this one. Then what the theorem says is, if the absolute value of the derivative at that equilibrium is less than 1, we have asymptotic stability. If the absolute value of the derivative at that equilibrium point is larger than 1, then we get unstable. And in the rare case that well, not so rare, we'll see. But in the case where we get the absolute values, they are exactly equal to 1, so that the derivative at that point is either plus or minus 1, we get inconclusive. And this is what's going to drive the next 2 theorems. Theorem 2 will deal with when the derivative is at positive 1, and then theorem 3 will deal with the case where the derivative at that point is equal to negative 1. So we'll state the 3 theorems first, then we'll do a bunch of examples on how to use these criterion to classify the stability or instability of equilibrium points. Let's do it. All right, theorem 2 is going to deal with when f prime of x star is equal to 1 specifically. So again, we're considering this difference equation. We have x star as an equilibrium, but now we've calculated the first derivative and put the x star in there, and we get exactly equal to 1. The first theorem, it's inconclusive. So now what we're going to do is we're going to get further conditions with more derivatives. If the second derivative at that point is 0 and the third derivative is negative there, we get asymptotic stability. Oh, Kitty's coming to join us. Kitty's coming to join us. If the second derivative there is 0 and the third derivative is positive, we get unstable. And if in general the second derivative is not 0, then we get unstable. So asymptotic stability happens when we get that the second derivative is 0 at the point and the third derivative is negative. Let's do one more theorem and then we'll recap. Then the last theorem, theorem 3, will deal with when the first derivative is negative 1. Let's do that. All right, our third and final result of this video is going to be consider the difference equation xt plus 1 equals f of xt, and now it's continuously differentiable. X star is an equilibrium point, but now we have the first derivative at x star is equal to negative 1. Then we have this weird thing, which is negative 2, the third derivative, minus 3 times the second derivative squared. If that thing happens to be less than 0, we get asymptotic stability. We can ponder, and I will attach a PDF, I'll pin a PDF to the proof of these types of things, but for now, we want to be able to calculate the first, second, and third derivatives, compute these things, and then determine whether we have stability or instability. So if this horrible thing, negative 2 times this third derivative at the point, minus 3 times the second derivative squared, if that's negative, we get asymptotic stability. And if that horrible mess is positive, we get unstable. At least now we have conditions for, regardless of the value, with these 3 theorems combined, we have conditions on checking whether equilibrium point is stable or unstable. Let's do some examples. All right, let's consider example 1, which is xt plus 1 equals xt squared minus xt plus 1. Last time we found the equilibrium for this, but what we have quickly is f of x is x squared minus x plus 1. Then we want to know when f of x equals x. So that's going to be if and only if x squared minus x plus 1 equals x. That's going to be if and only if x squared minus 2x plus 1 equals 0. And so we're going to get x minus 1 squared equals 0, or x star equals 1 is the only equilibrium point. Then what we can do is, now using our theorems, the cobweb diagram I drew, because that's going to give us insight. It looks like it's stable this side, but on this side it's unstable. This is what we're going to call semi-stable from the left, but in general this is unstable because it's moving away in this direction. How do we tell? From our theorems, what we're going to do is, first of all, I need the first derivative, which is going to be 2x squared minus 1. The first derivative at our equilibrium point is going to be the first derivative at 1, which is going to be 2 times 1 minus 1, which is 1. So we can't use theorem 1, we have to use theorem 2. What theorem 2 says then is I need this second derivative. Second derivative is going to be 2 which is positive, or f prime prime of x star is not 0. And so what that tells me is if the second derivative is not 0, that tells me by theorem 2 that x star equals 1 is unstable. It's semi-stable from the left, but in general, this is how we use this theorem. Or theorem 1 we can't use because the first derivative at the equilibrium point was exactly equal 1. Then we switch to theorem 2, which tells us when it is equal to 1. Then I use the second derivative and the third derivative if I need to determine whether it's stable or unstable. Let's do a couple more. Okay, for example, 2xt plus 1 equals xt squared plus 3xt. And I've drawn the cobweb diagram already, so you don't have to watch me do that. But it looks like we're going to get two equilibrium points, this one and this one, where they intersect, where the graph of f of xt intersects the graph of xt plus 1 equals xt. And that's going to be 0 and negative 2. How do we see that explicitly? F of x is x squared plus 3x. We want f of x equals x, which will be x squared plus 3x. That's going to be if and only if x squared plus 2x equals 0. So x star equals 0 or x star equals negative 2 are the two equilibria. To check these, what we want is what is the first derivative? F prime of x equals 2x plus 3. F prime prime, I don't know which ones I need, so I'll just compute them all. Then we're going to get f prime prime of x equals 2 and f triple prime of x equals 0. Once I have these three things, then what I want to do first of all is look at f prime of 0 is going to be 3, which is, so the absolute value of this is larger than 1. So this tells us by theorem 1 unstable. That's for the equilibrium x star equals 0. For x star equals negative 2, what do we have? We're going to look at, first of all, f prime of negative 2 is going to equal 2 times negative 2 plus 3, which is negative 1. So we know I can't use theorem 1 now. I have to use theorem 3. And theorem 3 says that we have to use this Schwarzschild. I didn't put it in there, but sometimes they call it SF, the Schwarzschild derivative. But we want to compute negative 2f triple prime of x star minus 3 times f double prime of x star squared. For us, that's going to be negative 2 times the third derivative is 0. Good. Minus 3 times the second derivative squared, which is negative 12. That was less than 0. So if that thing is less than 0, we get stable. So this is that x star equals negative 2 is asymptotic stable. So it's asymptotic, x equals 2 is asymptotically stable, and 0 was unstable. And this matches our cobweb diagram again, but this is just the more rigorous analytic way of showing this using our three theorems. Let's do one more at least. All right, as in the last example of this video, we're going to use xt plus 1 equals arc tan xt, which is definitely nonlinear. We have the cobweb diagram. It's already hinting that it's stable. This is a good way if you're doing this and you have to use the theorems and I force you to, or someone else forces you to use the stability theorems. The cobweb diagram is always a good way of intuitively thinking. I already think that 0 is the equilibrium and it is stable. How do I find this? First of all, what we need is f of x equals arc tan x. We are looking for when x equals arc tan x. We can prove using Rolle's and intermediate value theorem that there's a unique solution to this. 0, x star equals 0 satisfies this. Arc tan of 0 is 0 and x equals 0 is 0. And then there we can show that g of x equal arc tan x minus x has exactly one real root, namely 0. You can prove the contradiction, assume it has a positive or a negative real root, and you'll get a contradiction either way. So we won't use this g of x business, but long story short, there's a unique equilibrium. Long story short, there's a unique equilibrium, x star equals 0. And now what do I need? I need the first derivative for sure, which is 1 over x squared plus 1. That means f prime of 0 is going to be 1 over 0 squared plus 1, which is equal to 1. I now know I can't use theorem 1. I have to use theorem 2 because the first derivative at my equilibrium is exactly equal to 1. That means I need the second derivative. The second derivative of x is going to be the first derivative of this, which will be negative 2x over x squared plus 1. When we put that in there, I get equals f prime prime of 0 equals 0. Therefore, what do we need? We need the third derivative. F prime prime of x is 2, 3x squared minus 1 over x squared plus 1 cubed. I calculated these ahead of time. This takes more work than you think, but this is why we have to practice first and second and third derivatives. Now that I have this, f prime 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 of 0 is going to equal 2 times negative 1 over 1 cubed. So this is negative 2, which is less than 0. What does that tell me? Theorem 2 tells me that f prime prime of 0 equals 0 and f triple prime of 0 is less than 0. So by theorem 2, we see that x star equals 0 is asymptotically stable. And of course, this matches what our cobweb diagram says. Therefore, the moral is what we have to do is, in general, find the first, second, and third derivatives because we don't know which one we're going to do. First, I would compute the first derivative and then find out whether you have larger than 1 or less than 1 in the absolute value. If it's equal to 1 or minus 1, then we have to compute the second derivative and third derivatives to calculate and see whether these are asymptotically stable or unstable. Please subscribe right here, hit the notification bell. I'll see you next time.